Answer, reward if correct. Simple concept.
Simple concept, powerful results. But the authors point out some, let's say, significant hurdles when applying RLVR, especially for math.
Okay, like what?
Well, the first big one is data. High-quality math problems, especially those with detailed, human-verified solutions, they're just incredibly scarce.
And expensive to create, I imagine.
Hugely expensive, yeah. Think about having experts meticulously check long, complex mathematical proofs. It's time-consuming.
Makes total sense. What's the second issue?
The second issue is with synthetic data problems generated automatically. Lots of it exists, sure, but often it's made for, say, supervised fine-tuning.
Where maybe just having the problem and an answer is enough.
Right. But for RLVR, you need rigorously verified final answers. That's your reward signal. If the correct answer in your synthetic data isn't actually correct, well, you're rewarding the wrong thing.
Okay, so shaky ground truth for the reward signal. Got it. What's the third point? This is the one you said was central.
Yeah, this is where it gets really interesting. It's kind of the crux of their argument. Existing ways of augmenting data sets, creating more problems, often just don't consider what the model currently struggles with.
They just generate variations or mash concepts together.
Kind of, yeah. Without explicitly looking at the model's specific weak points at that moment in training.
And the result of that?
You end up generating a bunch of problems that are either, frankly, too easy, the model already knows how to solve them, or way too hard, the model fails them every single time.
Okay, so you're not hitting that sweet spot for learning.
Exactly. Neither of those extremes is very helpful for RL.
It's like trying to teach calculus by only giving problems that are either basic addition or unsolved conjectures. Not very effective.
Precisely. And they explain why this is bad for RL algorithms, like the GRPO they mentioned.
Right, the training signal.
It collapses. If the model always gets it right or always gets it wrong, the advantage, the learning signal in RL goes to zero.
So no useful feedback.
None. It just stalls the learning. Or worse, it can actually degrade performance because the model isn't getting meaningful gradients.
Okay, so training on problems the model finds trivial or impossible. Not helpful. Provides almost no signal.
That's the key limitation they're highlighting. But here's their, I think, really clever insight.
Mm-hmm.
Those problems the model consistently fails. They aren't useless.
Yeah.
They're actually incredibly valuable. They point directly to the model's specific weaknesses, like a diagnostic tool.
Your mistakes tell you what you need to learn, even for an AI.
Exactly that. So this leads them to ask the core question. How can we effectively use these consistent failures, these identified weak spots, to generate new training problems? Problems designed specifically to fix those deficiencies.
Can the model's own struggles basically create its personalized homework?
That's the essence of it. And that question leads directly to their innovation.
Which they call?
The SWS framework.
SWS. Okay, what's that stand for?
Self-aware, weakness-driven problem synthesis.
Self-aware, weakness-driven synthesis. Okay, that sounds intriguing. How does it work?
So the core idea is kind of flipping the usual process. Instead of just feeding generic data, they use the model itself during an initial training run to pinpoint what it's bad at.
Okay.
And then, based on those specific failures, the SWS framework synthesizes brand new problems tailored to target exactly those weak areas.
Like a personalized training regimen generated on the fly?
That's a great way to put it. The model takes a sort of practice test, the system sees where it consistently messes up, and then generates new practice questions just on those topics.
Okay, walk me through the steps. It's a pipeline, right?
Right, a structured pipeline. Step 1 is weakness identification.
How do they identify the weaknesses?
This happens during a preliminary RL training phase. They use an initial data set, say math 12K. As the model trains, they track its performance very closely on every single problem.
And how do they define a weakness? Just getting it wrong sometime?
No, it's stricter than that. They have a specific criteria based on the data. A problem gets flagged as a failed problem if two conditions are met.
Okay.
1, the model's accuracy on that specific problem never got above 50% during that whole initial training.
So consistently poor performance.
And 2, maybe even more telling, the trend in accuracy for that problem was actually going down over time, a negative slope.
Wow, so it wasn't just bad at it, it was potentially getting worse, or at least showing zero improvement. That really screams blind spot.
Exactly. Those flag problems become the seed problems for the next step.
Okay, step 2, targeted problem synthesis. Using these seeds to make new problems.
This is the weakness-driven synthesis part. The system analyzes these failed seed problems. It extracts the underlying mathematical concepts.
Like identifying it's struggling with, say, quadratic equations in algebra or maybe triangle congruence in geometry?
Precisely. They categorize these concepts, algebra, geometry, precalculus, etc.,
Yeah.
based on the paper's examples. Then, and this is clever, it strategically samples and recombines these extracted concepts to generate new problems.
Recombines them how? Just randomly?
No, not randomly. They try to ensure the new problems make sense. They look at things like how often concepts naturally appear together or use embedding similarities to make sure the combinations are coherent.
So it avoids creating mathematical nonsense.
Hopefully, yes. And here's another smart layer. The number of synthetic problems generated for each category isn't uniform.
Ooh.
It's weighted. Categories where the model failed more often during that initial phase, you get more synthetic problems generated for them.
Focusing the practice where it's needed most. Smart. But what about that issue of difficulty? Making sure these new problems aren't also too easy or too hard.
Ah, yes. That's addressed by a crucial substep within synthesis. Difficulty filtering. This is absolutely key.
How do they filter for difficulty?
They take the newly synthesized problems and feed them back to the model that just finished the initial training, the one whose weaknesses were just identified.
The intermediate model.
Exactly. They see how well that model does on these brand new problems. They run it multiple times, get an accuracy score for each synthetic problem.
And they only keep the ones in a certain range.
Precisely. They target a specific accuracy range. The paper uses 25% to 75% as an example. Only synthetic problems where the intermediate model's accuracy falls within that range are kept for the actual augmented training.
Okay, why that specific range? Why not just keep the hard ones if failed?
Because remember the RL training signal. Problems the model always fails, 0% accuracy, or always solves, 100% accuracy, provide almost no useful gradient, no learning signal.
Right, the signal collapses.
The problems in that middle range where the model gets it right sometimes, but wrong other times, those provide the strongest, most stable learning signals for RLVR. This filtering ensures the synthetic data is actually learnable and efficient for training.
So identify the persistent weaknesses, generate new problems focused on those concepts, and filter those new problems to hit that sweet spot of difficulty where the model can actually learn. That's quite a process.
It is, and that carefully curated set of synthetic problems, they call it XT, gets added to the original data set, XS.
Leading to step 3, augmented RL training.
Right. Now, the model that finished the initial phase continues its RL training, but this time on the augmented data set, XA, the original problems plus these new targeted difficulty-filtered synthetic problems.
And the goal is that this focused practice helps it overcome those specific weaknesses identified earlier.
That's exactly the hypothesis. Expose the model to learnable challenges right where it needs them most, aiming to mitigate those deficiencies and boost overall reasoning.
Okay, the framework sounds logical, quite elegant even. Self-aware, weakness-driven synthesis and filtering. But the proof is in the pudding, right? Does it actually work? What did the experiments show?
Good question. That's what they tested extensively.
What was the setup? Which models, which tests?
They used models from the Quinn 2.5 base series, testing at different scales, 3 billion, 7 billion, 14 billion, and 32 billion parameters.
So checking if the benefit holds as models get bigger.
Exactly. And they evaluated them on a really wide range of math benchmarks, things like GSMAK, the math dataset, Minerva Math, Olympiad Bench, even harder stuff like Gaokao, the Chinese college entrance exam, math questions, and competition math like AMC and AIME proxy.
Okay, a serious gauntlet of math reasoning tasks. What were the results? Did SWS make a difference?
The results were pretty striking. Consistently, across the different model sizes and all those benchmarks, the models trained using the SWS framework outperformed the baselines.
Baselines being the original models or models just trained normally on the initial data set?
Both, yeah. Compared to those, SWS provided a clear boost.
How clear? Were the gains significant?
Yes, quite significant absolute improvements. Get this. For the 7B model enhanced with SWS, they reported a plus 10.0% absolute average gain across the board. For the big 32B model, it was plus 7.7%.
Wow, 10% and nearly 8% absolute gains are substantial, especially on these kinds of reasoning tasks where improvements are hard-won.
Absolutely. And what's particularly telling is they saw really strong gains on the hardest benchmarks, a competition-level stuff like AIME.
Oh, really?
Yeah, comparing the SWS-trained 7B model to the standard RL-trained 7B model, they saw gains like plus 16.7% on one AV benchmark and plus 13.3% on another.
That's impressive. It suggests the synthetic problems generated by SWS aren't just fluff. They're high quality and challenging enough to push performance even on expert level problems.
It really speaks to the effectiveness of that whole pipeline, the targeted synthesis and the difficulty filtering. It seems to be creating genuinely useful, challenging practice.
And did they check if it actually fixed the original weaknesses, the problems the model kept failing initially?
They did. They looked at the 7B model again after SWS training, and they found a clear reduction in the proportion of problems from that initial data set that were previously flagged as failed problems.
So it learned to solve things it consistently couldn't before.
Exactly. They even pinpointed specific domains where gains were notable, like intermediate algebra, geometry, and pre-calculus, for that 7B model areas identified as weak spots earlier.
That closes the loop nicely.
And what's efficient about it is, these improvements happened even though each original problem was seen less frequently during the augmented training, because the data set was now larger with the synthetic problems.
Right, so the new targeted problems were doing the heavy lifting in fixing those weaknesses. It highlights the value added by the synthesis.
Definitely underscores the benefit of tailored, learnable practice over just more repetition of things the model struggles with ineffectively.
Really interesting. Did they push the idea further, explore any variations or extensions?
They did, yeah. They explored a few things in Section 4 that showed the robustness and versatility of the core weakness-driven concept.
Okay, like what?
Well, one was weak to strong generalization. They tried using a generally weaker model to act as a teacher, essentially, to provide the answers for the synthetic problems.
Using a less capable model to generate training data for a stronger one, how did that work out?
The key finding there was, again, the importance of their difficulty filtering step, because the weaker teacher might make mistakes, right?
Sure.
But the filtering step tends to weed out the synthetic problems where the teacher is most likely unreliable, often the hardest ones for the teacher, leaving behind a data set of synthetic problems that are still useful for training the stronger model, even with potentially noisy labels from the weaker teacher.
Huh. So the filtering acts as a quality control mechanism even for imperfect supervision. That's quite powerful. What else?
They looked at a self-evolving approach.
Letting the model do everything itself. Synthesis, filtering, the works.
Pretty much.
Yeah.
The model identifies its own weaknesses, generates problems, filters them based on its own assessment, and retrains. It shows promise, but they also noted limitations.
Such as?
Especially on very hard problems, the model might be biased in judging the quality or difficulty of its own generated problems. It might think a problem it generated is good or at the right level when it isn't.
Right, the classic challenge of self-assessment at the frontiers of knowledge. Can you accurately judge your own most complex creations?
It raises that interesting question about the limits of pure self-improvement loops. Maybe some external perspective is still needed for the toughest challenges.
Did they try applying the weakness idea without generating new problems?
Yes, that was another angle. Weakness-driven selection. Instead of synthesis, they used the identified weaknesses to select the most relevant problems from a large pre-existing pool of problems.
Ah, so using the weakness signal to curate existing data more effectively.
Exactly. And they showed this targeted selection based on weaknesses significantly outperformed just randomly sampling problems from that large pool.
So the principle holds targeting weaknesses is beneficial, whether you generate new data or select existing data more intelligently.
It connects the core idea to broader data curation strategies. And finally, they just doubled down on the impact of question difficulty.
Reinforcing the filtering point.
Yeah, showing again experimentally that the synthetic problems filtered into that medium to hard range, that 25–75% accuracy zone, led to much more sustained and significant performance improvements during training compared to easier synthetic problems. It really hammers home why that filtering step isn't just an add-on, it's integral.
And they included a specific example, a case study.
They did. It shows a concrete example, a geometry problem the model failed, the concepts like circle properties or triangle similarity extracted from it, and then examples of new synthetic problems generated at different difficulty levels, all revolving around those same concepts. It helps visualize the whole process.
Okay, so let's try and wrap this deep dive up. The main takeaway from this paper, this SWS framework,
is that it's a really innovative and, based on their results, effective approach to improving LLM reasoning. It does this by making the model, in a sense, self-aware of its shortcomings.
Using its own consistent failures to diagnose weaknesses.
And then using that diagnosis to drive the synthesis of new relevant practice problems.
Which are then carefully filtered to ensure they're at the right difficulty level for effective reinforcement learning.
Exactly. The results show clear performance boosts across different models, different benchmarks, especially the harder ones. It validates this weakness-driven training idea.
So this deep dive into the source material really shows how focusing on what a model can't do and creating targeted practice for those specific areas is a powerful way forward.
It moves beyond just brute forcing, with more data, towards a more intelligent, adaptive training paradigm.
So thinking bigger picture, what does this imply for the future of training these complex AI models?
Well, it suggests that maybe the era of just scaling data and parameters, while important, might need to be complemented by more personalized training.
Curricula tailored to the individual model's learning process.
Something like that. Training that adapts based on the model's own identified gaps and needs. It's a step toward more efficient and targeted learning.
It makes you wonder then, consider this, if AI models can get better at identifying their own blind spots and essentially generating the practice problems they need to improve, how might that change not just how we train AI, but could it even give us insights into how we approach human learning? Could we design more adaptive, weakness-targeting practice systems for ourselves?
That's a fascinating thought. Using AI development to potentially inspire better ways to handle our own learning challenges. Truly self-directed, adaptive learning, whether artificial or human.
Something for you to mull over until the next deep dive.